Hello again. This video is the story of the degree of the following number, e to the 2 pi I over n. This is an algebraic number. This is a root of a polynomial of degree n, namely t to the n minus 1. And the degree of this number is the degree of the smallest polynomial for which this is a root, the smallest polynomial with rational coefficients. And the proper title of this will be roots of unity, which this is one of them, and cyclotomic polynomials, which are eventually be these minimal polynomials for those numbers. So this is a complex number. This is cos of 2 pi over n plus I sine of 2 pi over n. This is one of the roots of unity. Let me recall the standard notation. Mu sub n is the collection of all of them, so collection of complex numbers which raised to the power n are equal to 1. And from trigonometric form, from this form of complex numbers, we can classify them all. They're labeled by, well, I can say integers, but really integers mod n. And in the earliest notations, they will be having this argument, 2 pi over n k times. So k again, can start with it as being an integer, but then really these complex numbers are periodic with period n. And moreover, when we multiply these complex numbers, will be closed, and the multiplication will still have, as a result of product of 2, we'll have another root of n, of degree n of 1. So this is a group, and when we multiply epsilon k and epsilon l, we will have epsilon k plus l. So that is a cyclic group isomorphic to this, and one of possible generators is this epsilon 1, which is just this number. So if we want to see the result of attaching this number to the rationals, which is the same as a quotient of the polynomials by the minimal polynomial, we will really have to accommodate all of them, because they come as soon as you let this number in, they all come. They are powers. Epsilon k is the kth power of epsilon 1, so they all come to the algebraic extension. Attaching epsilon 1 will be as good as attaching all of them, and the degree of this is the degree of this number. So let's start constructing polynomials for which epsilon 1 or all of them are roots. Well, obviously all of them are roots of t to the n minus 1, but if we're just interested in epsilon 1, we could make it smaller. So introduce the following n's cyclotomic, it is called, polynomial. That will be the product, or given by the roots. This is notation phi sub n. That will be the product of t to the t minus epsilon, and here we will just choose the roots, these epsilons, to be primitive roots of degree n. That means that their multiplicative order is exactly n. That means that they are generators of the cyclic group. So epsilon 1 is one of them, but there will be more in general. So that is the definition. We just take all the primitive roots of the n, we construct the polynomial by declaring them to be roots of this polynomial, and that is called the n-cyclotomic. So using this labeling by integers, we could write them by the condition on k. The order is n if and only if k is coprime to n. So that way we can count how many roots this nth cyclotomic polynomial will have, and hence what will be its degree. The degree will be the number of those k's. So let me just write it down. The degree of phi of n will be the cardinality of those integers mod n which are coprime to n. And that is called the Euler's function. This number is computed by the Euler's totient function. So the degree can be identified with the nth value of the Euler's function. Now we are going to argue that these nth cyclotomic polynomials are with integer coefficients. So a priori they are polynomials with complex coefficients. We are using complex numbers to define them. But you could quickly convince yourself that the coefficients have to be real, because with every complex root you will have a complex conjugate. Every conjugate of an order n root will be a root of order n. It will be the inverse. So easily this is a polynomial with real coefficients, but even more is true. So this is fact. This is just a fact. That these polynomials are polynomials with integer coefficients. And we will argue from a simple recursion, from a simple induction procedure. And the induction procedure will be controlled by just, as usual, by just logic. So let's look at this collection of all roots of degree n, of 1 in complex numbers. And let's not all roots are the same. So some have order n, some have orders which are less than n, and then they will have to be divisors of n by Lagrange's theorem. And let's separate this group into pieces which will be consisting of elements of a given order. So any order, any such order will be divisor of n, and then we will just group these epsilons by the condition that the order, multiplicative order of such epsilon is this divisor d. So then we could turn this decomposition of roots into product of polynomials. If we look at the polynomial for which all these numbers are roots, we will see t to the n minus 1. And then we will look at the polynomials for which all these numbers are roots for a given d, and that is the polynomial which we called the cyclotomic d-th polynomial. And then we'll have the easy formula that t to the n minus 1 is the product of all cyclotomic polynomials for divisors of n. And then I could run simple induction just by the sheer size of d, assuming that we already have this fact verified, and then checking that the last one, phi sub n, will have to be with integer coefficients, because it will be fitting into this product formula. So we could really write the answer for phi to the n as t to the n minus 1 over the product of all smaller cyclotomic polynomials labeled by divisors. So smaller means that the divisor d should be less than n. And by induction we know that they are all integer coefficients, and we know that they divide into this neatly, so that has to have integer coefficients as well. And that is it. So we already know that this is a polynomial with integer coefficients for which our epsilon 1 will be a root. And in the following lecture we will argue that this is actually an irreducible polynomial, so that will be the minimal polynomial of our number, and the degree as a result will be the Euler's function. So let's look at let's finish by looking at concrete examples of cyclotomic polynomials. By the definition, the very first one is just t minus 1. It just has unique root, the only complex number which has multiplicative order 1. 1. And using this induction procedure, the second will be seen as a ratio of t squared minus 1 and the product of all cyclotomics for divisors of 2. So divisors of proper divisors, not excluding 2. So the smaller than 2 divisors of 2 is just 1, and then we'll have to divide by t minus 1. Of course, the result is t plus 1. So what it says is negative 1 is the only complex number of order 2, and it is obviously true. The next, cyclotomic number 3, will have to be seen as t cubed minus 1 over, again, the product of all proper through all proper divisors of corresponding cyclotomics. 3 is a prime, so there is only one proper divisor, number 1. T to the first minus 1 we have to divide by, and using the geometric progression we have this answer. Next after, so that will be the first interesting polynomial. It will be the quadratic polynomial for which roots are primitive roots of degree 3. Complex numbers and primitive roots of degree 3. So for the cyclotomic number 4, we'll have to start with t to the 4 minus 1 and divide by all proper divisors corresponding cyclotomics. So that will involve 1 and 2. The proper divisors will be 1 and 2, so we'll have t minus 1, and then for 2 we'll have t plus 1. So both together they will give us t squared minus 1 in the denominator, and t to the 4 minus 1 divided by it will leave us with t squared plus 1. And of course, again, everything makes sense because the roots of these polynomial are plus and minus I, and they are the only roots of degree 4 on complex numbers. So finishing with the degree 5, 5 again is a prime, and the formula becomes particularly simple. It will be t to the 5th minus 1 over t minus 1, the only divisor of this prime 5 is 1, only proper divisor, so the cyclotomic will be of degree 4. Will be the sum of all powers of our variable. So that is it for now. See you soon. Goodbye.